Great. Hi, everybody. Welcome to our webinar today, Combi heat pumps. My name is Joe Wachunas. I'm a project manager at NBI. I'm here with Shannon Wilson and our two panelists who will introduce in just a second. So great to have you with us. This is a combined webinar with AWHI, the Advanced Water Heating Initiative, and New Buildings Institute. And the webinar is also developed in partnership with the San Diego Learn program. The Learn program is a San Diego-based workforce education and training program that is partnered with New Buildings Institute and AWHI to offer free energy efficiency and electrification webinars. Please visit the Learn website for more information and lots of great resources. It's www.sandiegolearn.com. Okay, so today we are going to be talking about combination space and water heating systems, also known as Combi systems. These systems seem really promising, one heat pump to rule them all, but they present a level of complexity that raises questions about their practicality and whether they'll actually scale on the market. Currently, the market features standalone heat pump water heaters and air source heat pumps. And today we'll be exploring whether it's possible to merge them together into a singular device and not sacrifice efficiency and cost. So there's a lot of field research underway, and we'll hear about that today. In Europe and Asia, there are many more market items available in Combi heat pump and heat pump water heating technologies. Products are available in the US, but they're in early commercialization stages, so we'll look at those, and they appear tailored for single family residential use. Some of the systems have cooling and others have add-on cooling. So today we'll discuss what are combination space and water heat pumps, what's their use case, and what are the barriers to their adoption? Why haven't they been adopted yet in mass? What's the current market for Combi heat pumps? Where are they in use today? What advancements, if any, are needed to bring more Combi heat pumps to market? And what are some stories and lessons from the field? And then we're going to do a deep dive into one Combi heat pump that's one of the earliest ones that's on the market, Harvest Thermal. So really look forward to that. Let me introduce our panelists today. Our two panelists, we're going to hear first from Edward Louie from the Pacific Northwest National Laboratory, PNNL. Edward is a building energy efficiency research engineer with PNNL. He loves all things related to building science, energy efficiency, and sustainability. You should check out his LinkedIn page where he posts amazing thoughts and articles and research on LinkedIn. His focus is on residential homes. For retrofitting millions of existing homes, Edward, like many of us, thinks that we need to first execute envelope improvements to improve air leakage, and then we need to meet the thermal loads with energy-efficient heat pumps for space conditioning and water. So Combi heat pumps, if possible. And then Pierre Delforge is the co-founder and head of product and operations at Harvest Thermal, where he's leading product design, development, and deployment. Before Harvest, Pierre spent 20 years in the computer industry and 12 at NRDC, where many of us knew him, and he led building decarbonization policy and advocacy. Pierre is passionate about making home decarbonization cost-effective and accessible to all. So thanks to you both for being on today. Really look forward to our discussion. Before we get started, if you have a question, please put your question in the Q&A box. Those are easier to track, and we'll try to answer as many as we can in the last 20 minutes of today's webinar. So Edward, with that, I'll turn it over to you and I'll drive your slides.
Thank you, Joe. Welcome, everybody. This is one of my favorite topics. I really enjoy being able to work on Combi heat pumps. So this slide deck, we're going to really do a kind of market overview into all the different products that are available, both like emerging in the US, as Joe said, and then ones that are available in outside US markets that are gradually coming into the US market. And then we'll transition to Pierre to do a deep dive on his system, the Harvest Thermal system. Next slide. So in this slide, we'll kind of look at terminologies, because we've used the word Combi heat pump, but the market, if you do the Google search, you'll actually maybe find other products if you do search with other terminologies. So we'll cover all the terminologies in this product category. We'll look at the history of Combi heat pumps, and then why would you care to go with a Combi heat pump system versus like a dedicated water heating system and a dedicated space conditioning system. We'll look at all the different kind of types or categories of Combi heat pumps, pros and cons of each, and then we'll look at market availability. And as I said, we'll transition over to Pierre to do a deep dive on his harvest thermal system. So next slide. So name and terminology. So when we say Combi heat pump, the industry has traditionally used that with a kind of a broad brush in terms of what it can do in terms of Combi. What are we combining? So some Combi systems can combine domestic hot water with space heating and space cooling, while others can only do space heating and domestic hot water. Even some more systems can do domestic hot water, space heating, space cooling, ventilation, and dehumidification. And then some other systems can do the space heating, cooling, domestic hot water, and integrate thermal energy storage. And later in the presentation, you'll learn why would you care to integrate thermal energy storage into a system. What are the advantages? And as in that second to last bullet, there's the different names. So when you're Googling for these types of systems, don't just use combination heat pump or combi heat pump. Also Google with the terms integrate heat pump or multi-purpose heat pumps. Those are some of the other kind of terminologies that will yield good results. And then different systems have the different capabilities to output different temperature fluids. And so that is kind of another kind of distinguishing feature of different products on the market is what type of temperatures can they produce? And then also controls. Are they systems that have very tight control where the manufacturer holds the control tight to their hand and makes it difficult for other technologies or products to integrate with their system, or it's simple controls that allow different other products to work with their system. There are pros and cons to each way to do controls. Next slide. So the history of combi heat pumps is really not new. Some of the earliest combi systems were in the even like before I was born, 1989. Carrier and EPRI developed a combi system. And then in the early 90s, Nordyne made an attempt at a combi system. Lennox made an attempt at a system. The system shown in the diagram on the right is a research system that never made it to commercialization, but it was a proof of concept. And that system was functioning and working in 2007. So yeah, it's not that new. And so the question is, why don't we have them today if these efforts were already underway decades in the past? And it has to do with that, like the technology, it was a little bit early for its day, so technology wasn't ready for prime time. The manufacturing capabilities for more complex systems just wasn't there. And the concern was for climate change isn't to the level it is today, and energy prices were much cheaper back then. And all that has changed. And so we have better technologies, manufacture capabilities. We're definitely more concerned about climate change today. We definitely have higher energy prices, no doubt. And so these types of factors that have changed will, I think, result in this time around, this effort to get combi systems to gain market traction. I think it'll take off this time. Next slide. So why combis? So some of the problem-solving capabilities of combi make it a really good value or product that could solve a lot of problems. So like one is that like a lot of homes have small or completely full electrical panels. And so then if you have systems where you need to add multiple new circuits, then that could be very expensive to upgrade the panel or upgrade the service entrance. And so combi systems have the possibility of being able to do domestic hot water electrification and space heating electrification all in one circuit. So if the home has a central air conditioning system, that those are typically 30 amp 240-volt circuits. Combi systems could take over and the air conditioning and just you reuse that same circuits, and then you can take care of domestic hot water, space heating, and space cooling all in that one circuit. So that would save a lot of money on the electrical upgrade side. Currently, heat pump water heaters are great for many applications, but there are some applications where some of the noise, cold air, and condensate generation it makes placing the heat pump water heater challenging. So the Combi systems don't generate any of these byproducts. So that could really increase the feasibility of heat pump water heating in homes where the current location of the tank is not ideal. And then high domestic hot water usage. So if you are a household that likes to take baths or even back-to-back baths, Combi systems have a much stronger heat pump that when it's sent over to the domestic hot water side can reheat water at much higher and faster rates. And so you get really good reheat rates. And then systems that have thermal energy storage integrated with the system can produce heating or cooling without running the compressor at a high level or even running the compressor at all. And so then if you have time of use rates, then potentially you can just run circulation pumps, which uses a lot less energy than the compressor, and then save electricity when the electricity is very expensive, during the hours when it's very expensive. And then, as we know, heat pumps work well, but during very, very cold, extreme hours of the day, in the coldest days of winter, or the hottest hours in the summer, heat pumps really do struggle still. And so with thermal energy storage, you could store up heat or cool in tanks during more mild hours of the day, and then use that stored heat or cool during the peak hours and save energy and gain cooling or heating performance as a result. So those are some of the really value proposition, cool reasons why Combi heat pumps just are awesome. Next slide. So this is a table that has not necessarily exhaustive a list of every product that's on the market, but it's pretty close to exhaustive. It's every one that I know of. And so and they're categorized to the different style of Combi heat pump. And you'll understand in later slides kind of why they're categorized this way. But there are these monoblock style heat pumps where there's a air to water heat exchanger in the outdoor unit, and then it's water or glycol that goes inside the building. Split heat pumps are like your traditional split air conditioner. You run a refrigerant line into the building. And then there's also split heat pumps that have heat recovery capability. And this heat recovery capability allows for simultaneous heating and cooling. So like you could have your domestic hot water being reheated at the same time the air conditioner is running. Other systems that attempt to do simultaneous heating and cooling, what they'll do is that the outdoor unit will actually switch. So like it'll work on recharging the domestic hot water tank, and then when it's done, then it'll switch back to cooling. And if you have two buffer tanks, then you can, at least on the experience side, experience what seems like simultaneous heating and cooling, but the outdoor unit is not actually doing simultaneous heating and cooling. So, and then some of the pros and cons of the different systems with the monoblock system, the main pro is lower refrigerant charges, less chance of a refrigerant leak because there's no field-made connections. The other two columns to the right of that, those systems require field-made refrigerant connections. So you'd really need a workforce that is good at making those connections, pressure testing, vacuum decay testing, so that those connections are solid. And with the refrigerant all located outside, then the monoblock system under the current refrigerant regulations and up and coming regulations, they have more refrigerant low GWP refrigerants available. Those refrigerants that are flammable or somewhat flammable. There's debates on whether they should go inside the building. It's interesting, that discussion, because we have natural gas going inside homes and people park cars with whole tanks of gasoline in their garages. So whatever. We can go to the next slide. And so air-to-water monoblock systems, as I said, you can use lower GWP refrigerants. These lower GWP refrigerants have good efficiency, as you can see in this graph here, where the y-axis is the cycle coefficient of performance or efficiency. So like, for example, isobutane, the big red circle in the close to the 0 GWP, good efficiency, low global warming potential. So that's an excellent refrigerant, but it has the challenge of being a red circle, so it is flammable. So there are some people that don't want this refrigerant going inside homes. That is not so much of a problem if it stays outside. So, which is what monoblock systems allow the heat pump to do, so that all the refrigerant stays within the outdoor units. And then it's glycol, that typically is the intermediate heat exchange fluid that goes in the building. One of the kind of cons of a glycol system is, if you look at the lower right-hand part of the slide, you can see that, like, okay, once you add glycol in the system, then you have some additional heat exchange. So like, normally it goes in a system, you go refrigerant over to indoor air, but in a monoblock system, you go refrigerant to glycol and then glycol to indoor air. So that additional heat exchange step, it's not thermodynamically free. So there is some efficiency loss as a result. We're going to go to the next slide. So this air to water monoblock category also has a lot of products. In the previous slide, we saw 2 different brands products. Here we have another 5. In maybe Joe in the intro mentioned that, like, a lot of these products are typically residential, but like, for example, the Mitsubishi EcoDan hydronic system, you can see in the graphics that that system is actually designed for multifamily, so larger systems where there's a rooftop air to water system, and then each individual EcoDan hydronic for each of the units in this multifamily would receive that, like, mid-temperature water, and then that mid-temperature water can then be either cooled or boosted up some more using the little heat pump compressor inside each unit. These systems also, a heat exchanger is really important. We'll get more into that in subsequent slides, but in the right-hand side of the slide, you see, like, you know, a tank that has a internal heat exchanger, and that heat exchanger is pretty large. It runs pretty much the entire vertical height of the tank. The other one in the lower part of the slide, by Chiltrix, at least in the diagram, it shows that the heat exchanger area is only in the, like, lower part of the tank. So regardless of what brand you go with, really kind of pay attention to the heat exchanger design. And later in the presentation, I'll kind of walk you through how to think about heat exchangers and evaluate heat exchangers, which is a really important part. Go to the next slide. So on the split heat pump combi heat pump systems, you can see, like, one of the pros is, like, there is not that intermediate heat exchange fluid. So, you know, we can go from refrigerant straight to indoor air, or refrigerant straight to the domestic hot water. So there's some greater efficiencies there. If the intermediate fluid is not glycol, then, and it's water, then there is a risk of freezing. But in the split heat pump systems, since it's refrigerant going to the outside, there's really no risk of freezing. Even glycol, if you mix like glycol at 10% and stuff like that, there is a temperature at which that glycol 10% mix will freeze. But refrigerants, the freezing point is so low that you don't have to worry about it. But one of the cons of these types of systems is because it's refrigerant going inside the building, then the number of approved refrigerants that can go inside the building, especially with the refrigerant GWP step down, is quite limited. Like right now, R454B and R32 are kind of the two refrigerants that are going to be replacements for R410A that can still go inside buildings. So more limited refrigerant choices. Here's two examples, LG's Therma V Split and Daikin Altherma 3R. As you can see, in these types of systems, there is choices for different indoor emitters. You can have floor consoles, concealed cassettes, wall units, and then we can go to the next slide. We can look at some more systems. Split heat pump systems can also do refrigerant to water in a heat exchanger inside. So like here in the Samsung system, they're diagramming that it can go into a radiant floor system. It can also go into panel radiators. Some of these systems are like kind of like the multi-split outdoor unit heat pumps. So there's multiple refrigerant ports. So you can have one refrigerant branch go into a refrigerant water heat exchanger that sits inside the house, and another branch can go to like a ductless heat pump head, for example. On the right-hand side, Mitsubishi has a few different lines, Mr. Slim, PUMY, PXZ. Those lines can all be paired with EcoDan, which is their name for a refrigerant to water heat exchanger. And in these graphics, you can see that you can have either multiple indoor units that are connected via refrigerants, or just one indoor unit that is more of a central refrigerant to air heat exchanger or air handler, and then the other branch being domestic hot water. Next slide. So with split heat pumps, there's an additional category, which is split heat pumps with heat recovery. There are far fewer products in this category. Panasonic, LG, and Samsung are the three that I know of. And these systems allow simultaneous heating and cooling. And that's made possible by a heat recovery unit that can allow for that. It's the 3-branch heat recovery unit that allows for really quite significant temperature difference between the heating side and the cooling side. And so you can be doing your domestic hot water reheat at the same time as air conditioning. And in theory, if you time it correctly, then the air conditioning waste heat can be heat recovered to go into domestic hot water. Unfortunately, these systems are configured for heat recovery for system in a situation where, like, for example, your basement is quite chilly because it's below grade, and so you may want that basement air handler to be in heat mode while your upstairs is hot, and so then you want that one in cooling, and so then the temperature difference between your cooling side and your heating side isn't that significant. But when you have domestic hot water paired with space conditioning, then the temperature difference between those two zones is pretty significant, and the out-of-the-box control logics on these pieces of equipment aren't currently optimized for domestic hot water and space cooling scenarios. But at PNNL, we're working with some of the manufacturers to optimize the control logic. So in the near future, we think that that control issue will be solved. There is definitely a higher cost in equipment associated with this heat recovery capability. So we're also hoping that in the future that the packaging of this type of equipment would be made such that the cost additional cost is reduced, because right now this type of system is really designed for light commercial, and that these manufacturers have what they've done is that they've just shrunken light commercial equipment down to residential sizes without really too much of a cost optimization efforts. But in the future, we think that the cost optimization effort can be an additional layer to make this equipment more accessible. Again, this type of equipment has field-based refrigerant connections. So again, skilled labor is required to install it in a leak-free manner. We can go to the next slide. In terms of market availability, almost all of these products are available in the US or beginning to be available in the US. They're definitely more common in markets outside the US, Europe, Asia, for example. So in terms of market readiness, so for the systems capable of heating and cooling, so basically all systems except CO2-based systems, some things to really think about is heat exchangers. So heat exchangers and tanks that are optimized for hydronic radiant floor are generally not optimized to do domestic hot water. And the reason is because the temperatures in the radiant floor are not going to be 120 degrees. So, or 130 degrees. They're much colder, generally in the like 80, 85 degree radiant floor temperatures. But if you want 130 degree water, those heat exchangers will result in very high liquid line temperatures. And so that very high liquid line temperature results in the heat pump operating not very efficiently. But in the heat pump water heater space, those tanks have figured out how to use refrigerants to heat domestic hot water to 130, 140 degrees while still maintaining reasonable liquid line temperatures. So we hope that in the near future, these Combi systems that use refrigerants in a split manner would maybe adopt tank designs and heat exchanger designs that have already been figured out in the unitary heat pump water heater space. And here's just an example in the lower right. The tank on the far right is one that's optimized for solar thermal and also being paired with fossil fuel boilers. And so that heat exchanger, as you can see, just doesn't have quite the surface area as the one on the left, which has very fine refrigerant lines wrapped around the tank. And then also when you have refrigerant, you generally don't want that heat exchanger inside the tank, because if you happen to have a refrigerant leak, then it could be your water might taste weird. To have some refrigerant oil in the water accidentally. So the way they get around with that safety issue is that they wrap the refrigerant heat exchanger on the outside of the tank. So if there is a leak, your water will still be fine.
Just a quick time check, maybe like 2 minutes.
Okay, great.
This has been
Yeah,
amazing.
so this is kind of my last slide. So and then for refrigerant to glycol systems, pay attention to the switching efficiency, because that intermediate heat exchanger fluid needs to actually get cold if you go from heating mode to cooling mode, or from cold to hot when you're switching the other way. For CO2-based systems, some things to note is if you have a weather condition where you live in a location where you may experience prolonged power outages during freezing weather, then take precautions to like maybe backup battery or something like that, because if you have potable water that has no glycol in it going to the outside, you could potentially freeze and blow up a heat exchanger. And then these systems are very sensitive to return fluid temperature. So if you have a system design, make sure that you're not returning high temperature fluid back to a CO2-based heat pump. And then there's currently no CO2-based systems that can do both heating and cooling. They're really optimized for heating only. You need a separate system for cooling. And then for systems that have integration with thermal energy storage, controls is something that's still being worked out, but the actual heat exchange thermal energy storage technologies are actually quite mature. We don't have to worry about like some exotic heat exchange thermal energy storage material that is currently not yet available. It's the software control logic that's currently being worked out. So we think that that will mature in the industry. And then really think about how long you want to store the stored energy to last. Do you want it to last 3 hours or 3 days? That has significant, impacts on the physical footprint, and the installation weight and the shipping weight. So keep that in mind if you are thinking thermal energy storage. And I think with that, we can go to the next slide. And I think the next slide is a transfer to my co-presenter, and he'll do a deep dive on the Harvest thermal system.
Thank you so much, Edward. Really appreciate that. That overview was incredibly, comprehensive and thorough. We got a ton of action going on in the chat and Q&A, so we'll want to check that out. I've got a lot of questions, but let's turn it over to Pierre. I'll stop sharing screen, Pierre. We'll turn it over to you, and then we'll probably, I'll say right now, we'll probably add an extra 5 minutes if that's okay, because we'll have a lot of questions to get to. So, Pierre, without further ado, thanks so much for being on, and look forward to your presentation.
Thank you, Joe. Thank you, Shannon, for hosting. And Edward, this was super informative. That's going to be my go-to reference deck for combis going forward. So I want to give you a practical example of a combi system. And it's a combi system with a twist. It has thermal energy storage. And the reason we build this combi system with thermal energy storage is to optimize for cost, for energy costs, both upfront costs by having a combi system for 2 end users, and energy cost by using thermal energy storage to optimize for costs. And the reason we want to do this is because heat pumps, adoption of heat pump at scale will require energy, cost effectiveness. It's especially for those of us who live in regions that have electric rates in excess of 50 cents a kilowatt hour, it's really important to be able to reduce cost and make sure that we have heat pumps are affordable for people to adopt. Just like rooftop solar, rooftop solar was adopted very at scale because it was saving people money on their bills, and we need to do the same thing with heat pumps. So let's start with the problem we're trying to solve. Heating and hot water, on average in the US, are responsible for nearly 2/3 of energy use in homes. So by addressing these 2 end users in one fell swoop, we can make a huge difference in people's energy bills and climate emissions. And together, those are also responsible for 10% of US climate emissions. And we can, the Harvest system can cut these emissions by 90% and at scale provide a huge climate benefit. I will tell you more about how we do this. Each Harvest system also reduces greenhouse gas emissions by between 50 and 100 tons over the lifetime, which is about twice as much as you'd get from switching from a gas to an electric car. So the solution to this 10% emissions problem is heat pumps, of course. They are almost magical in their efficiency, with 300% or more efficient. And this particular heat pump that I have on the screen here, the Sanco 2, which is CO2 heat pump, is particularly efficient with efficiency up to 550% in the best conditions, both because of the CO2 refrigerant and because it's an air-to-water heat pump. It produces 150-degree water, which allows for high storage density, so you don't need a lot of tanks. And typically 1 tank, maybe 2 will be sufficient. But generally, both for this and other heat pumps, there are challenges in scaling them at the pace and scale we need to meet our climate goals. And one of these challenges is really the time they run and the mismatch there is between the time they use electricity and the times when there's plenty of renewable energy on the grid. So this grid, if you put yourself in the shoes of a grid operator for a day, from midnight to midnight, like this particular grid in California or any other state that has a lot of solar, is going to have very low cost and emissions on the grid in the middle of the day when you have plenty of solar. If you live in a state with a lot of wind resources, it might be in the middle of the night or whenever you have most wind. But the point is, with renewable energy, is you're going to have a lot of renewable energy available at particular times of day and not so much other times of day. Unfortunately, heat pumps tend to operate when it's coldest, when people need the most heat. And that is often in the morning and in the evening, in the winter mornings before the sun rises and the winter evenings before the sun, after the sun sets. And therefore, there's no more solar energy on the grid, and therefore the costs and emissions in the grid are higher, which you can see in rates if you have time to use rates, or just generally in terms of the grid costs and overall rates. So what if we could run the heat pumps in the middle of the day on renewable energy and store that clean energy for when, and use it later when there's less renewable energy available on the grid? So that's what we designed the harvest system to do. So in green is when the harvest system uses energy right in the middle of the day if you have a solar dominated grid, or in the middle of the night if you have a wind dominated grid. And it's basically storing that energy for use later when there's when electricity is not as cheap and not as clean. So effectively, what we're doing is basically shifting the electricity use from heating and hot water into from peak to off-peak times of day, saving both emissions and energy costs. So how do we do this? Let's start with the heart and brains of the system, which is the controller box called the harvest pod. It's the heart of the system because it is a hydronic controller with a circulated pump, a number of valves, lots of sensors, and it's the brains of the system because it controls all the other components. And it has thermodynamic modeling, machine learning, optimization capabilities to optimize and to orchestrate when the system runs, to operate it at the lowest cost and emissions possible. So the first thing it does is controls when the heat pump water heater runs, turning on and off and how long. That heat pump water heater charges or heats the water in the tank up to 150 degrees Fahrenheit. And basically it's like charging a thermal battery. And that hot water is used for domestic hot water as well as in a hydronic fan coil for forced air heating, or for radiant heat as well, like radiant floors. And this is just like Edward said, CO2 heat pump only does heating, not cooling. So what we do is we integrate with either existing or new ACs or heat pumps to provide cooling. If you have a heat pump, then you can use that for supplemental heat as well to supplement the hydronic system. So you can go up to 4 tons of heating capacity, even though the Suncoast heat pump itself that doesn't can only go up to 2 tons with thermal storage by itself. So the key functions of the harvest pod are, one, to manage the thermal storage tank as a battery by monitoring state of charge, and basically optimizing when it is charged and making sure there's always enough hot water in the tank for occupants' heating needs and domestic hot water needs. And it also learns occupants' thermal needs based on the weather forecast, time of day, day of week. And based on that forecast and the weather forecast, it determines when people are going to need how much heat and hot water, and therefore what is the best time of day to charge the thermal battery to be able to meet those needs. So back to the life of the grid operator, and just how does this thermal battery work? So in the middle of the day, again, lots of cheap and clean electricity. So that's when the thermal battery is going to be charged. It's charging the heat pump is going to charge the thermal battery. Then in the evening, we're going to discharge the thermal battery to provide heat and hot water without running the heat pump as long as we have enough storage left. Now, in some cases, we run out of storage and then we'll run the heat pump. The occupant comfort and thermal needs are first priority, and load shifting is always second priority, right? So the heat pump will run on peak if needed, but most of the time it won't need to because thermal storage will take all or most of the load. And then at night, you may recharge the thermal storage if needed to top it up to be ready for the morning load. And then in the morning, you're going to start discharging the thermal battery again. So basically in the summer, when you have fairly limited thermal needs just for hot water, typically the heat pump will run maybe 2 hours in the middle of the day from 11 a.m. to 1 p.m. to charge on the cheapest, cleanest energy. And then you have enough hot water stored in the tank until the next day and repeat. In the winter mornings, or in the winter, when you need more heat and you don't have enough storage capacity to do 24 hours, run the heat pump both in the middle of the day and the middle of the night to be ready for both evening and morning heating peaks. So with this strategy, we achieve very high emissions reductions, basically by running the heat pump on clean energy and avoiding times of high emissions, up to 90% emissions reductions. And that's third-party verified on test sites. And from a cost-saving perspective, the bar is smaller, but it's not is as important, because from an adoption perspective, we need to reduce costs for people to be able to adopt heat pumps at scale beyond the early adopters who may be more affluent and be able to afford higher energy costs. So the load shifting that I mentioned early on is really what helped us achieve both higher efficiency, because we run the heat pump when it's warmest. As you know, the heat pump is more efficient when it's warmer outside, versus typical heat pumps that will run when it's coldest, because when people need the most heat. So there can be a temperature difference of up to 20 degrees, typically between morning and early morning and middle of the day. And that's worth about 100% efficiency for heat pumps. So typically 1 point of COP higher by running the heat pump when it's warmer rather than when it's coldest. You avoid defrost, you avoid a lot of issues that impact heat pump efficiency. So let's move to customer scenarios. So what are the customer scenarios that we see in the field and where people adopt this type of technology? So to date, we've sold over 200 systems, all the way from San Diego, all the way up to Edmonton, Alberta. Mostly on the West Coast so far. We are starting to expand beyond the West Coast, but so far we've been focused on the West Coast. And the majority of our systems sold today have been for furnace and AC replacements. People have a furnace and AC, they want to move to a heat pump, and they can do this with a harvest system for a similar cost to doing to a standard heat pump and heat pump water heater, and they will get 30% savings on their energy costs. The system itself, the harvest system, is a little more expensive pre-incentive than a regular heat pump and heat pump water heater, but it's also eligible for more incentives, starting with the federal tax credit for battery storage, which is 30% of total project costs uncapped, which is typically $7,000 to $10,000 per system, and it's quite a bit more than you would get with the $2,000 25C tax credit for heat pumps. So, and then states and utilities may have incentives. Like in California, for those of you in California, there's a lot of incentives available. In other states and utilities, there's also some incentives available. And when you look at all the incentives, the net cost, net of incentives, is about the same as a regular heat pump and heat pump water heater, and you'll get 30% cost savings. The other scenario that we see increasingly often is people who already have a fairly recent AC and furnace and want to keep it, but want to replace their water heater and use the water heater for hydronic heat. So it's an add-on scenario. We don't need to replace the AC by a heat pump. You keep it and you use the furnace for backup heat and the AC for cooling and the harvest system for hydronic heat and domestic hot water. So that's even lower cost. This is the lowest upfront cost electrification solution in the market because you don't have to replace the AC. Another scenario is people who already have a heat pump, maybe they were early adopters or they had it for some time, and they want to run it to shift when it runs to the cheapest times of day or cheapest and cleanest times of day. So then you add on the harvest system to the existing heat pump, and you benefit of the load shifting because of the thermal energy storage, as well as using the existing heat pump as backup and cooling. Another scenario is radiant floors and gas boilers. So as I mentioned earlier on, the harvest system can feed radiant floors and basically retrofit those to a heat pump with all the benefits of, again, load shifting and high efficiency for the Sunco 2 heat pump. And the last one is, if some of you are already adopters of the Sunco 2, we have a lot of fans and aficionados of the Sunco 2 heat pump, which is a really good heat pump, CO2 refrigerant. Then you can use that heat pump, you can keep it and make it go further by adding hydronic heating to it with a harvest pod. So it's very versatile, very modular in the way that it can be added or replace existing systems and be used in lots of different situations. Here are a couple of pictures of harvest systems in the field. On the left, a single tank system, which is 90% of our sales. Now, most people do one tank, the most cost-effective, gives you enough storage for the majority of your needs. And you see the harvest pod installed on the wall next to it, and the air handler right to a little bit on the left of the picture. So it all fits into a basement, typically where the existing water tank is going to be a drop-in replacement for the new storage tanks, a little bigger, but not that big, 28 inches diameter, fits into most closets and garages and basements. And on the right, you see a situation where we have two storage tanks. It's not very common, maybe about 10% of our sales, but for people who have space and want to optimize for costs and emissions, you get more storage with two tanks, and the system basically is even more affordable in terms of energy costs. So one of the questions I think that came up in the beginning of the webinar is, are there any compromises in getting Combi in terms of efficiency and cost? So I think by now you probably heard that, from a cost saving, probably not, but from an efficiency, I think what we've proven, and we have field data and third-party verified data to prove it, that we can operate Combi system at very high efficiency, on par with the highest efficiency heat pumps on the market. This data shows annual whole system performance around 3.0 COP, that's 300% efficiency, and heat pump efficiency at 370% average. And this is accounting for real worlds, not just the lab, COP number in the lab. It accounts for defrost, for people leaving doors and windows open, electric resistance coming in if needed. So this is on par with the very highest efficiency heat pumps you'll find in the market. And in addition to those, we shift load, which allows for cost reduction on time of use rates. And this really matters because, if you want to provide affordable solutions, we need efficiency as well as load shifting for cost optimization. Last slide, I wanted to show the load shifting concept. So these are results from a pilot study we did with Peninsula Clean Energy up in the Bay Area, where we deployed 4 homes for an entire year. They were monitored for an entire year. And you can see here the average day for each home over the entire year. So this is the average day for the whole year. And you can see in green, the green bars are the heat pump operation, which is largely off-peak. So green, yellow, red are the peak prices on time of use rates for PG&E. So in some cases, nearly 100%, in some cases, 90% of the load was off-peak. And then depending on the home, some of them had almost no usage on peak at all for 9 hours from 3 p.m. to midnight. Some of them had a little bit of usage. Those were early versions of the system that didn't have the backup heat pump. They only had the Sanco 2. So the Sanco 2 in some cold winter days had to kick in at night, in the evening a little bit to meet the load. But on average over the entire year, it was about 90 to 100% load shifting off peak. And that gives you access to the lowest cost electricity to run your heat pump off the lowest cost and cleanest electricity and avoid the high cost and high price hours. So in summary, the Harvest system is a 3-in-1 heat pump: HVAC, domestic hot water, thermal storage, thermal battery. It reduces energy costs by 30% compared to regular heat pumps, and gas, depending on local gas and electric rates, up to 90% climate pollution reduction, and grid friendly, which is important as we want to scale this technology, that we make sure that we keep the grid affordable and we don't cause increases in electric rates by increasing peak demand. Thank you. I'll be happy to take questions.
Thanks so much, Pierre. Thanks, Edward. Really appreciate it. We've got lots of questions coming in, so we'll try to get to as many as we can. And questions, I think both of you can answer questions for you individually. So let's dive in. I think the first one, maybe this is for both, and it goes back to Edward. You had the market availability slide. Folks are just wondering, are these, we know that Harvest is available in the US, and then Edward, can you speak to, are any of those split systems that you mentioned, and especially with the heat recovery, are any of them available, on the market now, or if not, any timeline on their availability?
Yes, so they are available, both the LG multi-VS heat recovery system and also the Samsung DVMS Eco heat recovery units are available. they're, like I said, like with market availability, they're emerging. So like, I don't think you're gonna just walk into your supply house and ask for one. They have one already on the pallet ready to sell you. There might be a longer lead time, but they have AHRI numbers. They are available here in the US, even the heat recovery units. Some of the split non-heat recovery unit ones are not yet available here in the US, but we should see that, I think, begin to change maybe this year or early next year.
Great. And then Pierre, maybe to you, you said most of your installations on the West Coast. Is it, is there plans to kind of, are you launching there and then going nationally, or what are the plans for kind of distribution throughout the US and North America?
Yeah, we are expanding strategically based on market demand and utility partnerships. So what we're looking for is, markets where the utility is interested in helping deploy this technology. It's, it's important for us to be able to do this in partnership with a utility or other, market, development organizations to help, be able to grow the market effectively.
Okay. Great. It kind of leads into my next question on, the availability, but availability also of workforce. We know that there have been some stops and starts that Edward highlighted in this industry. What does the workforce look like for these split systems that are, might involve plumbing, electrical, HVAC, all those systems? Do you see challenges with workforce? Pierre, you probably can speak to that firsthand, and then maybe we'll start with you, and then Edward, I'd love to get your thoughts on the workforce for these systems.
Yeah, the Harvest system really leverages standard installation skills and the standard HVAC, standard plumbing and electrical. Depending on the state, it may be part of the same installer, or maybe it's two installers and one sub to the other. But typically what we see is regular HVAC installers who install Harvest systems just like, alongside any other system. And it doesn't take any particular skill set. It just takes about a 90-minute training to understand how things together and how to, which sequence of events, but it's fairly simple. And we have very comprehensive documentation online. If any of you on the audience today, just go on our website and you'll get to the contractor page and documentation, and you'll see a lot of detailed diagrams that show you how to install a system.
Edward, any thoughts on workforce from your end?
Yeah, I think these systems, the brands are not maybe your most common brands on the market, and so there's maybe a learning curve associated with understanding how to install them, and the control side is perhaps the main challenge to figure out. But that's not really a unique problem to Combi systems. As we get into like even heat pumps in general, having installers understand the controls and take the time to set up the controls correctly is just a general industry training thing that's work in progress. And then on the refrigerant split systems, it's not a unique challenge to Combi systems, but just heat pumps in general, anything that has field-made refrigerant connections, the workforce. There are people who are excellent at making field-made connections, but there are still some that need to be trained up to the industry best practices on how to make field-made refrigerant connections.
Yeah, we experienced that in my house recently when we were having our heat pump repaired and saw the connection. Lots of refrigerant leaking from there. Great. So question on cost. Pierre, fascinating that Harvest, I'd love to hear first, like, how did Harvest Thermal get, how were you able to qualify for the battery storage tax credit? That's news to me. That's fascinating. And I could see that 30% tax credit could help bring it in line. So curious there. And then maybe for Edward after that, just installed cost on these systems compared to your separate heat pump and air source heat pump. So first to you, Pierre.
Oh, so the thermal or the battery storage credit, which is 25D, the section 25D of the tax code, basically specifies that you have to have 5 kWh of storage capacity for a system to qualify as battery storage. It does not require specific technology like electrochemical or other. And so it basically, our system meets this 5 kWh requirement and meets all the other requirements of the law. So it's from that perspective, it's just like solar or a standalone battery, which since IRA, standalone batteries are eligible for that 25D tax credit, and as a result, thermal storage forms of batteries can be eligible as well. Interestingly, as well, we've talked a lot about single family, but these systems are also possible to install and targeting multifamily dwellings with individual systems like garden style apartments. And there's another section for multifamily property owners called Section 48, which explicitly calls out thermal energy storage. And again, it's a 30% investment tax credit for multifamily property owners to be able to install this technology on their properties.
That's great. Edward, any thoughts on your end on
on cost, as I mentioned, the not having to upgrade a service panel, circuit breaker panel, or service entrance wiring for adding more circuits. I think that those cost savings could, be then transferred over to some of the higher cost Combi heat pumps, at least for now. I think in the future, Combi heat pumps will really cost incrementally more than a straight space conditioning heat pump. So I think in the long run, there will be cost savings from the service entrance, not having to do the service entrance upgrades. And then Combi heat pumps, another kind of way that it could add some cost is a lot of the Combi heat pump configurations I showed allows for zoning. And so that's a added feature. So like, reconfiguring a home's heating system to allow for zoning certainly adds cost. But all those systems you can pair with a multi-position vertical air handler and just stick with a traditional, one zone central ducted system.
Okay, perfect. Thanks. So this is a question for maybe the monoblock systems, and Pierre, we can start with you since yours falls under that category. Someone was asking, how much space does all the hydronic equipment, the piping and the pumps take up? And we saw a couple of the pictures there, but is that would you see that as a challenging point, the space requirements for the hydronic systems?
No, we haven't really. I mean, there's always homes that are really cramped and don't have space, but most homes that we've been dealing with have found ways. I mean, typically, if you look at the harvest system, the storage tank goes where the existing water heater tank goes. The air handler goes, replaces the furnace, and then you just add an outdoor unit, which is a side discharge, so a suitcase form factor. Which is relatively easy to fit either on the ground, or you can mount it to the side of on the wall, onto the side of the building. So it's pretty easy to fit in most situations, and there's always no exceptions where you cannot. But the majority of our cases, we haven't had any concerns with that. And all the controls are in the box. The harvest pod is kind of a shoe box size device, so it's pretty easy to fit right on next to the tank on the wall in the closet. And again, we haven't had any challenges with that mostly.
Great. Edward, any thoughts on what you've seen on space challenges, if any?
Yeah, so space challenges, the split heat recovery systems currently all utilize what a heat recovery box or branch box. Different companies all use different names for that box, but those boxes are not that small. And one thing that makes that installation of that piece of equipment challenging is they typically have straight piped requirements. So like something like around 20 inches or 16 inches of straight pipe going into the heat recovery box. So you can't have a bend right at the connection. And so those systems are more challenging in terms of space. But in the future, we hope that there will be heat recovery boxes built into the outdoor units. So then you then no longer need to worry about figuring out the space for that in the indoor environment. And then for monoblock and just straight non-heat recovery split systems, I don't see space challenges to be an issue.
Okay. Thank you for that.
I mean, if anything, on the water heater side, you can save space by not having as tall of a tank. Like unitary heat pump water heaters are fairly tall, so you can save some space there. And then not having any sort of air volume requirement could result in pretty significant space savings also.
Right. Okay, perfect. So just a quick question. Do installers need EPA refrigerant handling certifications to install the monoblock systems?
I'm not aware of that requirement.
And Pierre, do you know with your system, do they need a EPA certificate?
No, so our system is water-based, so there's no refrigerant, at least in the Sanco 2. So
yeah. Okay, perfect.
Just plumbing, standard plumbing.
Right. Well, on that note, with the water-based, John's asking if these systems, could Harvest operate in Colorado climate zones 5 through 7 at altitude with like lower winter temps, or with the water-based system, or would be a refrigerant or glycol-based be more recommended for those colder climates? Pierre, maybe.
Yeah, so with the Sanco 2, it is portable water throughout, and in the outdoor unit. So the Sanco 2 manufacturer has detailed recommendations for how to protect against freezing. First is that they have controls that circulate the water whenever it gets cold. And in the case of a power outage, somebody on the chat said that there's drain valves that operate mechanically that don't need power to basically run water through the lines whenever if there's no power. So there are freeze protection measures that can be taken, and that's why we have system installed all the way up to in Edmonton, Alberta right now. And with the right freeze protection measures, it should not be an issue.
Okay. Thanks for that. Okay, well, I think we can do our last question here and kind of looking to the future. Edward, maybe we'll start with you. What do you see as the next steps to bring more products to market? Is it driving consumer demand? Is it working out additional technical challenges with the systems? What will help Combi heat pumps over the next 5 years?
I certainly think a test standards for a Combi heat pump would be really helpful, because right now the integrated domestic hot water space conditioning efficiency, there's not a standard for manufacturers to test so that everybody can display their numbers on equal footing. The test standard would, I think, be kind of challenging, because you have to make some assumptions about climate zone, and also make some assumptions about typical domestic hot water usage patterns. And then for heat recovery systems, then the exact kind of test schedule for domestic hot water could significantly change the efficiency numbers, because if you have the majority of your hot water usage occur in the peak cooling period, then you could potentially get better numbers there, or even some sort of large enough tank where you can defer heating the tank, because there's still a column of hot water at the top of the tank until the peak afternoon. So, I mean, the test standards would certainly be a great help, I think, as the next step.
Thanks, and thanks for that, Edward. And then Pierre, any thoughts? What will Harvest does have? You have access to the 30% battery storage tax credit. I'm sure that was a big boost. But what would facilitate Harvest and other manufacturers to increasing market share with the system?
Yeah, the technology is available, and the incentives are available. So I think this is the right time now. We just need adoption and more contractors to sell these systems and know how to install them, and more customers to be aware of them. Awareness is a big barrier today. I mean, the Combi systems are not common, as most people don't know of them. So when they have a need to replace their furnace or their heat pump or their water heater, they won't necessarily go and look for a Combi. So we're making sure that the Combis are part of what the standard solution set. It's a lot of market development, which I think we need right now to scale the market, because everything else, both the economics work today. The economics are very compelling. The technology is available, proven, high performance. I mean, it depends on the technology, right? It's all in the controls and the design of the system, but at least there are some systems that can, like Harvest, can be very high performance and very low cost to run. But it's a matter of market development to get those adopted at scale.
Okay, well, thanks so much. We'll leave it there. Huge thanks to Edward and Pierre for their fantastic presentations. Thanks, Shannon, for running the back end. Thanks to you all for joining us, and thanks to San Diego Learn for helping us put on this webinar. We'll send out slides and recording, and look forward to seeing you on another webinar. Thanks all. See you soon.
Wonderful. Thank you. Bye-bye.